Dan Jacoby lives in a small town called Kedima in central Israel. In 1994, he came to this site. This is the story of what he found that day.
בשלישי למרץ 1994 קיבלנו ידיעה מחבר שלנו שהוא טייס אולטרלייט חובב, שהוא הסתובב כאן באזור וראה עיגול נחיתה. העיגול הוא בערך ליד השיח שמה לפני עץ האקליפטוס. ובאנו לכאן, קבוצה של חוקרים, להתחיל לבדוק מה הולך כאן. מצאנו עיגול נחיתה קלאסי בקוצר של 12 מטר. היו כאן ממצאים נוספים, אתה יכול להסתכל על התיק שלי, אני פותח אותו. ברבים מאתרי הנחיתה בקדימה מצאנו אבנים כאלה. אפשר להסתכל מקרוב. זאת אבן שבדקנו, היא עשויה בסיליקון. ברבים מהאתרים היו אבנים כאלה בכמויות משתנות. עם הזמן היו כאן נחיתות נוספות. עוד 4-5 נחיתות בדיוק באותו שטח. במאי 1994, והיה בתוך האדמה גוש גדול מאוד, שזה רק חלק ממנו, של חומר ירוק, הוא קל, מוזר, ולקחתי את הגוש, הגוש גדול מאוד.
Hi, I'm Dr. G'Rald Tani, the director of this film. Usually, I'm only in the credits, not in the movie. However, my professional background as a physical chemist prompted Dan Jacoby to ask me for my help in analyzing the samples that he found at UFO sites 26 years ago. I took up the request, if only for the scientific challenge. Scientific projects always begin with a literature search and ask the question, has anything similar been found or been reported? And if so, what tests were performed? What results were found? Now, in this case, about a year prior to Dan finding his samples, a similar finding was reported in the Negev desert.
את האבן הזאת אני מצאתי באזור שקרוב למכתש רמון. אני קיבלתי לפני כחצי שנה עשרות טלפונים מחיילים היסטריים שבחרו לי בטלפון. מסתבר שהם היו במסע ניווטים, באור יום, ופתאום ראו דיסק ענק, כסוף, עם בטן ועם גיבנת כזאת, גולש מעבר לגבעה סמוכה אליהם, ונעלם, וכעבור 2-3 שניות ממריא למעלה. לקחתי את קבוצה של מדענים, הגענו לאותה גבעה שהחיילים תיארו לי היכן היא נמצאת. וקודם כל, הדבר הראשון שמצאנו זו פלטה ענקית של זכוכית שנוצרה כתוצאה מחום עצום שהוקרן כלפי מטה. מצאנו גם את האבן הזאת ועוד 3 בגודל הזה, והיו שם עוד אלפים קטנטנות, ממש בגודל של ציפורן. אין חומר כזה בטבע על פני כדור הארץ, וזה כתוב במסמך של הטכניון.
The rock found by David Ronen was based on pure silicon. Dan also claimed that the analysis on his rock was performed by a geology lab and came back as pure silicon. So here we have 2 very similar reports of pure silicon rocks by different people at 2 UFO landing locations hundreds of kilometers distant from one another. In the form of silicon dioxide or silicate salts, silicon is amongst the most common elements in nature. However, as the purest element, Si, it's only been known for about 200 years, since Berzelius discovered a process to convert sand into what is known as metallurgical grade silicon, which is about 98% pure. Now, samples of metallurgical grade silicon are sold on the internet and look exactly like the rocks that were found at these sites. Sites selling UFO site rocks prove their special connection to UFOs by showing the fast rate at which ice will melt on the rock. However, this effect is related to the very high thermal conductivity of silicon, and any chunk of metallurgical grade silicon will show the same effect, as we see here. Now, the way to know if Dan's sample is simply metallurgical grade silicon is to use a device called the scanning electron microscope, or SEM. This allows you to examine the sample at high magnification and to simultaneously obtain the weight percent of every element present in the area under examination. How does it work? This is a simple cutaway of a typical SEM. First, the gases inside are pumped out to achieve a high vacuum. An electron gun at the top under high voltage creates a stream of electrons that are focused by the magnetic lenses on the sample at the bottom. Now, electrons from the beam knock out electrons from the atoms encountered, which are collected and used to create a picture of the scanned surface. Some electrons penetrate deeper and are absorbed by atoms that then emit an X-ray. The X-ray's energy is specific to the element, so that by measuring the energy and amount of the X-rays emitted, we obtain the type of elements and their weight percent in the area examined. To use the SEM, we needed to cut a small piece off of the Dan's rock. Now, because of silicon's hardness, a diamond disc saw is required to do the job. Fortunately, Yair Ashkenazi, the glassblower at the Weizmann Institute, was willing to help out. The next step was to order 2 hours of SEM time with Dr. Einat Zellinger at the Center for Scientific Imaging in the Faculty of Agriculture of the Hebrew University in Rehovot. Einat attaches the sample to the base with conductive tape, and we are ready to go to the scanning electron microscope. After inserting the rock sample, she turns on the pumps for evacuation of the chamber, and we get our first look at the material. The diamond disc has mashed the surface, making it relatively featureless. The white line in the box on the bottom shows the length of 0.05 centimeters in the picture. We find a hole in the surface with a crystal in its depth. Einat raises the magnification so that the white line now represents 0.002 centimeters, and we analyze the elements present in the area of the little yellow box up above. The analysis comes back. As you can see in the black box below, the crystal is 98.9% silicon and 1.1% indium. We go back to low magnification and analyze the surface. This time, the answer comes back with 1.2% oxygen in addition to 97.5% silicon and 1.2% indium. So Dan's sample certainly isn't metallurgical silicon that can be bought on the internet. Now, although the indium concentration is about double the maximum normally used in silicon doped with indium, that combination is known in the semiconductor industry for infrared light sensors. Then a few days later, our analysis fell apart. At the suggestion of a geologist friend in the department, Einat examined the sample in an optical microscope that illuminates the surface with 3 different wavelengths of ultraviolet light and shows fluorescence in the presence of certain elements. Although a low concentration of indium in silicon should not show any fluorescence, Dan's sample lit up like the night sky when illuminated with all three wavelengths. Where had we gone wrong? We had ignored the lanthanide family of rare elements. In order to save analysis time, the SEM's program ignores the lanthanide elements unless you specifically request to examine for their presence. So we marked the area analyzed in the UV microscope with some dots with a pen so that we could identify that area in the SEM, and then redid the elemental analysis at low magnification with the lanthanides requested this time. 13 of the 14 members of the lanthanide family showed up with a cumulative weight percent of almost 38%. I've created these separate tables from the original results because of the difficulty in reading them in the original table. Amongst the lanthanide elements found is 4% thulium, which has a value of $3,000 per kilogram. The non-lanthanides present are 2% oxygen, 8% carbon, 51.7% silicon, and 0.29% indium. The low oxygen content is very significant because it means that virtually all of the lanthanide metals are in the pure state, as opposed to oxides or salts that are normally found in nature. We moved to a new silver-looking area that had small crystals. It showed only 0.29% of lanthanum and 2.8% of ytterbium, with large amounts of iron and titanium. The composition varies considerably at different spots and is not homogeneous. Once again, the metals must largely be present in their pure form because the oxygen concentration is too low for all of the metals to be present as oxides. The heterogeneity of the rock composition is like that found in meteorites. However, the elemental composition has nothing in common with those normally found. Note the high oxygen content of meteorites. In addition, the lanthanide family content of meteorites is the order of hundreds of parts per million, and not up to 6% as in Dan's material. So let's summarize what we've learned. Dan's rock is definitely not metallurgical silicon, and the number and concentration of pure lanthanide elements present is unlike any known industrial material. The elements are heterogeneously distributed, changing from place to place, both in elemental composition and in the weight percent of the elements found. Then, the rock is not a meteorite. Although it is heterogeneous, it has far too little oxygen, and the concentration of the lanthanide elements is about 100 times that ever found in meteorites. So, while we can't prove a connection to UFOs, no conventional explanation has been found to rationalize all of the observed facts. Additional analyses of similar finds at other sites could strengthen the connection to UFOs. Our work on the samples continues, especially on the plastic material, which has only just begun. As we generate results, I will create additional films to bring them to you. Anyone wishing to help this project can do so in several ways. First, more samples of finds from UFO sites are needed. If you have such material, use your phone to make a short video showing the sample and giving a description of the details of how and when it was found. Send the video to the MUFON Israel website. Second, research costs a great deal. Just for example, time on the SEM costs $150 an hour. All donations help push the work forward. Those should be made to MUFON Israel. Instructions are on the website. And third, if you are a chemical professional who's willing to help with the analysis of the plastic material, please send your CV to the MUFON Israel website with a description of what tests you could perform and what size sample you would require. So that's it for now. I look forward to doing the next chapter of this film, and perhaps working with some of you who are watching.